time on my clock. Daniel, are you okay to start?
I'm fine.
Great. So let me start by introducing myself. My name is Rudi von Steiger, director at ESA, and I'm your host for the ESA Game Changers online seminar today with Daniel Müller. The topic of today's seminar, as you can see here, is SOHO, the sun from SOHO, 25 years of SOHO, and first glimpses into Parker Solar Probe and Solar Orbiter. Daniel has a PhD from the University of Freiburg in Germany. He worked at the Kiepenheuer Solar Observatory there, and he was later a Marie Curie Fellow in Oslo, went over the pond to Goddard, where he became deputy project scientist for SOHO. So he's uniquely positioned to give us that talk today. Coming back to Europe, he went to ESTEC, where he is today as the project scientist for the Solar Orbiter mission. His talk today is primarily about SOHO, but I'm sure he will tell us a few glimpses in the end about Parker Solar Probe and Solar Orbiter. And that's particularly timely because just yesterday was the first public release of data from Solar Orbiter and the release of the Astronomy and Astrophysics special issue on Solar Orbiter. So, Daniel, we are thrilled to have you here, and we are looking forward. All 173 of us are looking forward to your talk today. The floor is yours, Daniel, or rather the screen is yours, I should say. Please go ahead.
Thank you very much, Rudi, for the kind introduction. And it's a real pleasure for me to be with you this afternoon in a virtual way to talk about SOHO. And SOHO has really at least shaped my life personally. And I've been fortunate enough to work on the mission when it was still in its, well, not in its childhood, but in its mature middle age days. And it's now been a quarter century that we've been blessed by SOHO observations, and it clearly led the way. And in that sense, I think it really fits into this series of game changer presentations. It'll certainly be a challenge to cover nearly only the most important aspect in 45 minutes. SOHO has already led to almost 6,000 journal publications. So it'll be a very selective view. I try to mix a bit classical results with more recent results based on SOHO data. So let's get started. I will first give you a brief overview of what SOHO is as a mission, and then address the three main science objectives that SOHO set out to tackle. That's investigating the solar interior by means of helioseismology, studying the outer atmosphere of the sun, the corona, and the further out corona, the solar wind, and finally touching upon some peculiar things in the solar wind, not only coronal mass ejections, which we are quite familiar with, but also comets that SOHO has just fortuitously been able to observe in large numbers. And then I'll close with a few slides each on Parker Solar Probe and Solar Orbiter. SOHO, like Solar Orbiter and Ulysses before then, is a joint mission of the European Space Agency and NASA. The SOHO spacecraft was built in Europe and then launched by NASA in December 1995. And it's been operated from Goddard Space Flight Center by a joint European-American team since then. And the spacecraft orbits the Lagrangian point L1, which is 1% between the Sun and Earth distance in an equilibrium point that it orbits around. That gives it an uninterrupted view of our mother star 24/7, so it's a perfect place to be. It was conceived for a nominal mission duration of 2 years, and that has been exceeded by quite a few years by now. And it has 12 instruments on board. 7 of those are still operational. Some have been superseded by more advanced and more recent instrumentation, for example, on the stereo missions and more recently on NASA's SDO mission. But overall, there's still unique data coming out of SOHO. And as late as last week, the US Congress even passed the Space Weather Act, where they said that SOHO shall be operated as long as it produces useful data. So it's an interesting legal aspect as to whether the US Congress can pass a law that deals with the fate of our European-built spacecraft. But I think all that we care about as scientists is that SOHO will be kept running as long as it produces useful data. So we hope that can be another few years. Who knows? SOHO's instruments provide a wide range of data products. So first of all, we provide UV images of the sun and spectra of the sun, both on disk and off disk, or at least for many of the 25 years SOHO did. It provides measurements of the surface of the sun as seen in visible light and its magnetic field with the MDI instrument, and nowadays with NASA's HMI instrument on SDO as a successor. It measures the composition, the chemical composition of the solar wind and energetic particles, and last but not least, total solar irradiance, which is a very important data product to really get a long and uninterrupted time series of what the sun does to be compared with, for example, temperatures on Earth. Okay, given that this is a wide audience, I thought I should have one introductory slide about what the sun is actually. So the sun is a relatively standard star, G25 star, relatively middle class in terms of mass and age. It has a nuclear fusion reactor in its core where it fuses hydrogen into helium at a core temperature of 15.7 million degrees. The energy produced is then transported outwards by means of radiation, so photons being emitted and absorbed and re-emitted in the inner 70% of the sun. And the outer 30% is what we call the convection zone, where energy is transported by means of turbulent motion. So a little bit like boiling water in a pot. And that upper surface of the convection zone is then what we call the photosphere, which we see in visible light. And there you can see these so-called granules, which are patterns, a bit like the Rayleigh-Bénard convection patterns from the turbulent motions in the convection zone. So the sun is hot on the inside and cool on the outside, relatively cool, 6,000 degrees. And the surprising thing is that this star, like many others, is then surrounded by a very hot corona that has a temperature beyond 1 million degrees. And it's still not exactly clear whether there's one or several mechanisms to get the corona to this high temperatures, but clearly SOHO has been playing a key role to investigate the mechanisms. So let's start from the inside. We want to take a look in the solar interior. How do we do that? The second part, I will talk about the outside, the corona. Why does it exist and how is it heated? And the final part on SOHO is about the solar wind. So let's start on the inside. How do we look inside the sun? The way to do it is a technique that is similar to something being used on Earth to look at the interior of our planet. You use sound waves and their perturbations by internal structures. So in the case of the sun, the interesting aspect is that as a star that's composed of ionized gas, a plasma, you have a sort of a wobbly sphere that can be excited to resonance oscillations around an equilibrium. And you have competing forces. You have gravity pulling inwards, and you have radiation pressure pointing outwards. And as the net effect, you end up with a body that can be excited to a multiple number of modes, like a musical instrument, like a bell. So from the turbulent motions in the convective envelope, you can excite a whole spectrum of frequencies. And so this is a very exaggerated view of one of these modes. So this entire gaseous sphere is then swinging in a particular mode, and there's a superposition of many of these modes. So the way we look at that is we take images, time series of images of the surface, and measure the vertical motions by means of the Doppler shift of a particular line of iron. So by measuring the displacement of that line with respect to its rest wavelength, we can deduce vertical velocities on the surface. And that can then be used as an input to a Fourier decomposition. And you can invert the frequencies to get the structure of the solar interior. And on this plot on the right, you see that there are multiple modes of sound waves bouncing around with different length and probing different depth of the sun. And the bottom line is that the frequency resolution that you get in your entire spectrum of waves is proportional to 1 over the duration of the time series. And that tells you why SOHO has been so valuable for helioseismology, because it could really provide a very long and almost uninterrupted time series of data. The only way to do that from the ground is to have a network of telescopes with a similar setup. And there have been several of those. And one in particular, the Gong network, has been very, very successful as a network of instruments to complement SOHO data. Among the first really key results of SOHO that are still being cited frequently is a paper from Jasper Schrau et al. From 1998. They looked at the sun's differential rotation. So the sun doesn't rotate as a rigid body, but it rotates more quickly at the equator than at the poles. So if you sit on the equator, it takes you 25 days for one revolution. Close to the poles, it's almost 10 days longer. And now this pattern could be derived from just studying small-scale features on the sun's surface. But now the question is, how does that pattern continue under the surface? So now we can use this technique of helioseismology to look below. And the result is quite surprising, because I mean, in this plot here, you see color-coded the rotation speed, and these isocontours show that in the outer shell, the convective shell of the sun, you have constant differential rotation effectively along radial cuts, not along cylinders. If you looked at most numerical models of the solar dynamo in these days, they would predict that the sun would rotate effectively along cylinders concentric with the solar rotation axis. And that was an interesting result, that the same type of differential rotation continues all the way down to the what is called the tachocline. And this tachocline is an interesting region where the radiative zone transitions into the convective zone. And that's a region of enhanced shear. And that's also where we believe these bundles of strong magnetic flux are tangled up and then rise to the surface and ultimately form sunspots. So the tachocline is a region where things happen. And you can see that clearly here, because this is a clear region with a strong gradient. And the other region where it deviates from this radial dependence is the surface. And also there you observe a lot of shear. Now, what really amazes me, and I have to say that I'm not a helioseismologist really by training, is how well the observations of SOHO matched the models of the sun as a star. And what you see here is the difference in the squared sound speed between a standard solar model from Christensen-Dalsgaard and observations from SOHO. So the differences are less than 0.5%. And these are actual error bars. And you can see that there's even an explanation for this peak, and that's exactly at the height of the tachocline. Because of the enhanced shear, they suppose that there's enhanced rotational mixing in this area. But overall, it just really tells us that the solar models are quite accurate in terms of the global physical parameters of the sun. And the second aspect is the rotation as a function of depth. So in 3 different latitudes at the equator, 30 and 60 degrees latitude, they measured the rotation as a function of depth. And also here you see what was clearly seen on the previous slide. At the depth of about 0.7 solar radii, you transition from a relatively constant rotation rate to the near solid body rotation rate. So differential here and solid body in the inside. And these three arrows mark the values measured from tracking surface features. So they match quite well. And the strong gradient in this area corresponds to the hump here. And the fact that these curves take a strong turn close to the surface indicate that you have a lot of turbulence and shear near the surface, because that's where the star suddenly encounters the cool space. Okay, another really amazing topic that I find peculiar is related to the fact that we've seen in the previous slide that solar models are well known and established, and we know from data that they are correct. There's been this puzzle about neutrinos and their types for many decades, and it even made it into public, popular science literature. It was number 2 in the list of top science stories in 2002. So the story was that from key experiments, namely the Sudbury Neutrino Observatory in an old mine shaft in Canada, and the Super Kamiokande experiment in Japan, they found peculiar things. They found in Japan that the muon neutrinos you would get from galactic cosmic rays created in the atmosphere would be detected less if you looked at night. Now, neutrinos are, second to photons, the most prevalent particles in the entire universe. They permeate everything. Per square centimeters, you have about 700,000 neutrinos per second. Every square centimeter of us is being permeated by that number of neutrinos. So you wouldn't expect a strong discrepancy whether or not you look at the sky or the sky looks, or the neutrinos come from the bottom through our planet. But they saw a strong decrease. And in Sudbury Neutrino Observatory data, they found about a third of the electron neutrinos that they expected. Now, the only way to explain that is by invoking neutrino flavor transitions. And those, in fact, had been not considered widely before, because they in turn imply that neutrinos have a mass ever so small. But combined with the seismic models from SOHO and Gong data that really showed that the sun as a star and the main producer of electron neutrinos in the solar system could give you a particular number of electron neutrinos. So you had a good confidence that this was really the number of electron neutrinos coming. And when they checked with the SNO data for the total of all 3 types of neutrinos, they found that the total was exactly as expected to come from the sun. And the depletion of the electron neutrinos had to do with them changing flavor into the other 2 types. And that ultimately led to the Nobel Prize in Physics for the 2 lead people from SNO and Super Kamiokande. And SOHO played only a bit role in that, but still it's quite impressive that the sun is the source of all the neutrinos that we find here. Okay, this is a nice new result from SOHO based on old data. It's about the meridional flow, and it's a recent work from this year published by Lagrangian and colleagues in Science magazine. The meridional flow is a sort of conveyor belt mechanism that drags the magnetic field along and is influential for the solar cycle. So the basic concept is that over the duration of a solar cycle, you need to transport magnetic flux from the equator to the poles, and somehow this flux needs to be recycled and end up back at the poles in some way. And you would expect that it takes place below the surface because you don't see it above the surface. So now the way to look at it is to, again, use helioseismology and the sound waves and the way they travel. So if you have these 2 points marked on the surface, A and B, you would expect that waves should travel a little faster with the flow than against the flow. Now, the challenge is that these travel time perturbations are tiny. They are on the order of a second or less. And that's why the meridional subsurface return flow has been extremely difficult to measure. measuring the poleward flow on the surface is still difficult, but doable. You can just track small features like bright points in X-rays or magnetic elements and calculate an average flow. But below the surface, you really need to invoke a large time series of data. And that's what these authors did. So they combined 23 years of data from MDI and the ground-based GONG network. And they measured the meridional flow for the first time unambiguously and in detail. They could even determine that the flow geometry is a relatively simple one. It's a single flow cell per hemisphere. And the return flow that they measure has a speed of 4 meters per second at 45 degrees latitude. So that's about the speed of a small boat or a slow cyclist. And the impressive thing is that really, if you picture yourself in a small boat in the meridional flow, if you integrate the entire flow cell, it would take you about 22 years to get back to where you started. And that's exactly the duration, the average duration of the solar cycle. So this result really supports the concept of the magnetic flux transport dynamo model, and really has for the first time an explanation as to why the sun's activity cycle is on the order of 2 times 11 years. So now I would like to take you a little further out into the sun's hot corona. I want to start with this movie from 1.5 solar cycles ago. It's from the so-called Halloween storms in 2003. At that time, I was a PhD student, and I had to give a seminar at a colloquium of other PhD students that had nothing to do with physics and natural science in general. But I could show some movies from the Halloween storms, and everyone liked it, and they could say, yes, we really understand why it's important to study the sun. So that really tells you that the general public is really receptive to SOHO's data products, and you can use that really to piggyback some scientific education on top of it. And what you see in these movies is UV pictures of the sun. And the LASCO coronagraphs C2 and C3 on the outside, and you see these streamers where the solar wind comes out, and in between you see coronal mass ejections, and some of those are directed in towards SOHO, and then you see a kind of snow of events where energetic electrons hit the CCDs of the LASCO detector, and occasionally you see something like that. SOHO people know that this is a planet, that there are still people out there who believe that we've been observing lots of UFOs, but we would simply conspire with NASA not to tell people that they exist. So SOHO has really provided daily movies of the sun in a way that people could relate to, and that's one of the things that you can't really express in papers, but it's something that well, people know the sun, even though they might not think about it on a daily basis, but I think we've really educated at least some part of the public about what the sun is, thanks to SOHO data. So these are images from the EIT telescope in helium-2 304 that shows the transition region at about 60,000 degrees. And here you see the corona of about 1 million degrees, magnetic loops traced out by hot plasma emitted from iron 8 and 9 at 17.1 nanometers. Now, the question about the heating of the sun's corona inevitably has to do with magnetic flux, and it has to do with the emergence of magnetic flux on the surface, and the fact that if you move magnetic field around, you will eventually tangle the magnetic field lines, and at some point these field lines get under stress, and this magnetic energy stored in stressed field lines can be released by means of magnetic reconnection. So here's a movie of a magnetogram of MDI. If you zoom in, you see really constant motion of the 2 different magnetic polarities, and if you picture flux tubes rooted in these dark and bright spots, you can immediately picture that these will eventually have to give way to some energetic events that then reconnect the polarities, because otherwise the magnetic tension would get too high. Another thing that was first seen on SOHO are the so-called EIT waves. I mean, these are waves named after an instrument just because no one knew initially what they were. They'd only been seen in EIT. You can see here a flare and then some sort of dimming with a front extending, but it's very faint. If you do a difference movie of the individual frames, as you can see on the right, you see a massive front erupting from this location of the flare, spanning almost the entire sun. And the interesting thing here is that it shows that local changes in magnetic topology can really have a global effect on the entire star. So these waves have high speeds between 200 and 600 kilometers per second. They are typically deflected by sunspots. They are also deflected or even stop at the boundaries of the coronal holes. They happen a lot. They've been associated with fast mode alpha shocks. And there have been really hundreds of studies since, in particular then with higher time resolution data from first stereo EUVI and SDO AIA. And they really started a new field of coronal seismology, where people use effectively waves of this type to study the physical parameters in the corona. So the emission in the corona is so faint that you can't really do, let's say, easily spectral polarimetry with the lines because they are optically thin and in emission. But if you really want to measure the flows, then the best thing is to take spectra and use the Doppler effect. So that's what also could be done with SOHO. If you combine the UV images with SUMA spectra, you put the spectrometer slit here, people could really measure Doppler shifts corresponding to flows of several hundreds of kilometers per second in these coronal loops. This slit I just showed is from the SUMA spectrometer on SOHO. It's an amazing instrument that has performed really the most detailed analysis to date of the UV spectrum of the sun in this spectral range. It identified over 1,000 emission lines. Some of those had not really been seen before. And the SUMA team has produced an atlas of spectra of both the quiet sun, the coronal hole, and the sunspot. And in later days, they also published an off-disk version of SUMA data as well, showing the emission in the off-disk part of the solar corona. And that's a fantastic way to do physics. Sometimes, if you just look at images, there's a tendency to just start getting involved into pattern recognition, but with you can develop diagnostic tools to measure physical. So this has been important, both the solar and stellar, and Alpha Centauri A overplotted an average SUMA. So this is one of the more difficult slides of our presentation, because I think it can take spectra of the outer corona, really faint, and when measuring extremely high temperatures of more. Okay, am I still connected?
Yeah, we just lost you, but now you are back.
Okay.
Sorry, Daniel, the audio was chopped at times, but I think then you were kicked out. Now it seems better.
Okay. I didn't do anything in particular, but no. I hope it continues.
It was just the last minute or so, so please just continue.
Okay, very good. Okay, so what do we see here? What we see here is
Could
the
you
difference.
You
share
still
your
need
screen,
to
please?
share the screen.
I'm not sharing the screen?
No.
Okay. So. So, share screen. Okay.
Looks good.
Okay. All right. So, welcome back. I'll do this slide again because it seems like I've been lost in digital space. This is a slide that shows you remarkable aspects of the temperatures in the outer corona. SOHO could measure that there's a strong difference between temperatures of electrons, protons, and heavy ions in the corona. And that indicates that there is, at least in these instances above coronal holes, an wave heating going on via ion cyclotron resonance. And that is a selective heating process that essentially doesn't heat electrons. It heats protons and it heats heavy ions even more. And if you look at this line shape here in the bottom right from UVCS, the crosses are the actual measurements. It looks really peculiar, but it can be fitted quite well with a combination of a wide Gaussian that corresponds to extremely high temperatures of about 200 million degrees, and a little narrow Gaussian in the middle. And that, in fact, is stray light from the solar disk, from the very nicely measured sharp spectral lines from the 06 doublet on disk. And we'll get back to this later on because it really helped to explain some aspects about the acceleration of the solar wind. So this is a plot of the average temperature as a function of distance from the sun. There are, of course, models that tell you what the average temperature should be according to the given model. But of course, ultimately, you want data to confirm or reject a particular model. SUMA data has provided good constraints close in, and UVCS could provide good data a little further out, a few solar radii away, and you can really see that there are different populations, that there are ions that are much hotter than protons in the corona. And then there's a big gap, and then you had data from the 1970s from the Helios missions in this regime, and there are models that indicate what the emission what the temperature should be, for example, of 06 in the outer corona. And this is, I'm just showing this plot because it shows why Solar Probe and Solar Orbiter will be really key, because this is really the area where these two new missions will go. We have good data until here, and we have very little here and nothing in between. So this is why it's going to be very interesting to see what SOHO will find when it gets into the nominal emission phase. Okay, now we look at the solar wind. Where is it actually accelerated and how? Now, we found that, well, it has been found that the solar wind comes in different types. There's typically the fast solar wind and the slow solar wind. The fast solar wind usually emanates from magnetically open regions like coronal holes. And an early result from Don Hassler and colleagues published in Science showed that you can see clear blue shifts in the coronal hole compared to red shifts in the quiet sun. And the largest outflow occur at the boundaries of the so-called chromospheric network that's indicated here in black. And so it was explained like solar wind breaking through the chromospheric network like grass around the edges of paving stones in a patio. So I think that's quite a nice analogy. The difficulty here is, of course, you're looking at polar coronal holes. So the foreshortening is quite strong because you're in the ecliptic. And that's really why we are extremely excited about the polar views from Solar Orbiter in the later phases of the mission, because that should really improve this view and give us a better picture. Now, in terms of where the solar wind is accelerated, UVCS really helped to put limits on where the acceleration takes place. And they found that most of the solar wind acceleration should really take place in the very low corona. And for example, 06 already reaches 300 kilometers per second a few solar radii away. And that's going to be very interesting to compare with solar probe results when they get to their inner perihelion of around 10 solar radii, to what extent they still see solar wind acceleration at that distance or not. For the slow solar wind, that's typically associated with streamers. It has a different chemical composition as well. For the slow solar wind, Neil Sheely and colleagues used small blobs or inhomogeneities in LASCO data to trace the solar wind, a little bit like leaves on the river. And they found a constant acceleration taking place also at a relatively small distance from the sun, with a sonic point at 5 solar radii. So also here, I'm really interested in seeing what solar probe will find, whether they find a sonic point that is significantly outside of the perihelion that they will be at, or whether to some extent the acceleration is already finished at 10 solar radii. Now, and here I was talking about solar wind composition. There's the Celia's MTOF instrument on SOHO that could really give you the entire beautiful wealth of atomic physics in the solar wind. It has provided many first measurements of ions in the solar wind, and also a few other elements that have been measured before, but simply are not included in many other solar wind instruments. So now, when we go back to this composite movie of the sun's corona and solar wind, the fact that SOHO could provide really daily images and movies of the sun and the corona gave it a real practical role in terms of almost a space weather forecasting mission. And so the data products have been made available more or less in real time, so that people could look at the data. And the thought was, we can even use that to make predictions about effective events close to Earth. It's of course difficult because the particles travel fast, but in a particular application, Arik Posner and colleagues looked at radiation storms. So what you really worry about if you're an astronaut is not to be doing an EVA or other activity where you're not sitting behind the water tank of the ISS when you have a radiation storm that could expose you to energetic ions. So in this study, they used the fact that electrons are accelerated much more quickly and to faster speeds than protons because of their lower mass. They could use SOHO COSTAT data to generate a forecasting method that provided at least 1 hour of advance warning. And that's a method that the Johnson Space Center is now using routinely. The solar maximum of 1.5 cycles away really provided us with a lot of energetic events that we are only dreaming about now. So I hope that the next solar cycle will give us at least a few of these. You can see how a flare on the sun gives rise to coronal mass ejections and then energetic electrons seen at SOHO. And in some cases, even the auroral oval being extended all the way to the latitudes of Florida. And Bernard Fleck, the SOHO project scientist, told me that this was a day when he could see the northern lights clearly from his home in Washington, D.C. And one thing that has not been possible in the past, 20 years ago, was really to put this all together and use it as input for numerical models. So with the Moore's law and progress in computational resources in the last 25 years, what can be done now is really very different from what could be done 20 years ago. So in this study, Tibor Törek et al. Used significant amounts of data from SOHO and TRACE, ACE, and the WIND spacecraft to model the magnetic eruption of a complex active region that gave rise to these so-called Bastille Day flares and events, and then trace out the entire chain of events from the magnetic reconnection in the low corona out into the solar wind. And even though that is, let's say, a numerical approximation of reality, it shows us that we've really come a long way in terms of understanding the entire system of sun and the sun-Earth space in between. And I mentioned earlier that SOHO already also played a surprising role in the field of comets. SOHO has, by means of its LASCO coronagraph, discovered more than 4,000 comets. And the impressive thing is that the vast majority have been discovered by citizen scientists. So not by people that work on SOHO full time, but really by people that download SOHO data to their computer and analyze it and look for things that are different from what they would expect to see. And so there's been a number of really interesting results in cometary science based on SOHO data or partly based on SOHO data. For example, about the dust production of sun-grazing comets, the outgassing rate, and even the size of a comet nucleus, for example, in this case of C2001, C2. Often these nuclei of sun-grazers are very small, but there's one that the comet C99 Linear, where by combining SOHO data with Hubble data, they could detect or derive the comet nucleus size of almost 400 meters. They could derive the entire amount of water released. And they could also estimate the density of that comet nucleus. And I'm always amazed when I look at that number. It's about a third of the density of styrofoam. This is an animation from NASA's Science Visualization Studio, and it shows the different types of comets. We have the Kreuz group sun-grazers, the Maya sun-grazers, and other comets. And what always makes me smile is that these comets are visitors from the far reaches of the solar system and beyond. And even though SOHO is a solar mission, it can snap some pictures of these visitors when they come, and then they go again. And but we have some nice pictures, and some of them even come back. Now, a last comet slide is this one, on the detection of the shadow of a comet. The SWAN instrument on SOHO maps the entire sky in the UV light of the sun emitted in Lyman alpha that irradiates the entire heliosphere around it. And the fact that comets are usually surrounded by large clouds of hydrogen can clearly be seen here. You can see a huge cloud around that comet. And you also see something else. That's a black spot here. And that is really peculiar and had never been seen before. And it can be explained by this sketch below, that you have the sun that illuminates the heliosphere and makes it glow in the glow of Lyman alpha, except that area where you block out the UV light because of the Hale-Bopp hydrogen cloud. So that explains why the black spot is here. It's the shadow of a comet, and the shadow is 1 astronomical unit long. Okay, I can't do this talk without pointing out that without a little bit of luck and a large amount of concerted team efforts, most of the SOHO story would not have happened. And that is related to the fact that in 1998, the SOHO spacecraft was lost, and it was not clear at all whether it could be recovered. It wasn't clear whether the orbit had been disturbed, to what extent it was spinning, and in particular, the transmitter and receiver temperatures were unknown. Now, those are, of course, key. If you want to send a signal to SOHO and listen to it, you need to know at what frequency you need to be looking. And so it took 4 weeks of looking to not find anything, and some people had already given up hope on finding SOHO back, with a notable exception of Roger Bonnet, who was back then ESA's director of science, who had overseen the selection and implementation of SOHO. Roger was adamant that you must continue looking, and there must be a way of getting it back. And I think that's really what spurred people and gave them the extra motivation to keep looking. And there was a first glitter of hope based on a detection by the Arecibo radio telescope that some of you might know from a James Bond movie. They used it in reverse mode to fire a radar pulse at the direction where SOHO was expected, and they did detect an echo. And based on that echo, they could derive that the fact that SOHO was rotating in a way that it would only get sunlight on its solar arrays for a tiny part of its spin period. And the bottom line was that some instruments had gotten very hot, some had gotten very cold, and most of the propellant had frozen. So the challenge was to thaw the tank with the power of a light bulb, but it could be done. And in the end, SOHO regained its sun pointing attitude in September 1998 and could be recommissioned with almost all instruments intact and working well, except for one part of the LASCO coronagraph. And you can see the first picture of EIT here. The orientation isn't quite right yet, but it's working and the quality is great. So people were over the moon. It wasn't the end of the adventure though, because a few months later, the last gyroscope failed. And so engineers were really struggling to develop a completely new way of an attitude and orbit control system to stabilize the spacecraft without gyros. And even that worked, and it's been working really well ever since. And in the end, more than 160 people were involved from the space agencies, the prime contractor, the ESN network, to make this remarkable recovery happen. And I think it really speaks for the team, but also for the role of someone who could really lead people and make them believe in the task at hand. And I think that's a special thank you to Roger Bonnet. This episode happened before I was involved in SOHO. I was still a student, but clearly my life would have turned out differently if SOHO hadn't been brought back. So in a way, I think Roger gave SOHO to the community twice, not only for having it built in the first place, but for making the recovery possible. Thank you. Now, I'm almost over time, so I wanted to spend still a few slides on Parker Solar Probe. It's one of the missions spawned in a way also by SOHO's Success. It launched 2 years ago and has 4 instruments on board. It just set a new solar distance record of less than 1/10 of an AU last week. It is an elliptical orbit that uses Venus to get closer in over time. And I would just wanted to show you 2 first glimpses. There's one was the question about the presence or not of dust close to the sun. There's an interesting physical effect that says that if there's dust in a particular size range that is not pushed outward by radiation pressure, it should slowly spiral into the sun and create a dust-free zone. That's been predicted 100 years ago. It hasn't been seen in the past, but there's some hints of a dust-free zone around the sun from early WISPER data. That's the wide-angle coronagraph built by Russ Howard, who also built the LASCO coronagraph on SOHO, and the Solo High coronagraph on Solar Orbiter, for that matter. And the second thing that most of you picked up probably last year at the AGU fall meeting are these switchbacks. These seem to be persistent folds in the magnetic field that have been detected in the radial magnetic field and then correlated with the radial velocity. And the interesting thing is that they see large fluctuations when they get close to the sun. So this is time, and this is the radial magnetic field. This is time, but also the distance. And these reversals did not correspond to crossings in the heliospheric current sheet, but indeed, they seem to be kinks in the field that travel outwards, and that they could relate to propagating alpha in waves. Now, at the very end, a little bit about SOHO. As I said, it's SOHO. Well, Solar Orbiter stands on the shoulders of giants. Rudi said that already. We had the first public data release yesterday, as well as a special issue in A&A with mission and instrument papers. What is Solar Orbiter about to do? We try to connect the sun and the heliosphere. We don't get as close to the sun as Solar Probe, but we get as close as we can while still pointing cameras and spectrometers at the sun. So we do simultaneous in situ and remote sensing measurements. And the interesting aspect is that over time, we're also in an elliptic orbit. We use Venus to get out of the ecliptic plane and eventually to 30 degrees to get this polar view that I mentioned before. And there'll be interesting configurations to do lots of interesting science, both with ground-based telescopes or telescopes in near-Earth orbit, and also other telescopes like stereo and solar probe that are elsewhere in the inner solar system. Now, this is first images and measurements that you might have picked up in July. It's not the time here to talk about them in detail, but the one thing I wanted to point out is the fact that you can, in fact, connect remote observations and in situ measurements. If you measure spectra in the corona and you detect the same ions in the solar wind, which we are trying to do with the solar wind analyzer, you should be able to really connect particular packages of the solar wind to their source regions on the solar surface. This is the last slide really on the milestones. In December of this year, we'll take the first flyby at Venus to gradually adjust our orbit to get close to the sun. And about 1 year from now, we'll be visiting Earth for one last time, about 440 kilometers above our planet, to then take a left turn and get right into the sun inside the orbit of Mercury in spring of 2022. And there's a web page where you can look at where SOHO is on a given day. And I wanted to end here and just close by playing that movie and say that from my perspective, the way SOHO has really spawned a series of new missions was not only by its results by itself, but also by showing the way. Clearly, I mean, there were spectrometers and imaging instruments at higher resolution that could be built 10 years later because technology advanced and you knew what worked and you knew what could be improved. But the fact that someone tried and put this all together in a comprehensive mission for the first time, I think that's really the legacy of SOHO. And these are images from SDO. That's really the offspring of SOHO. And I hope that in a few years' time, we'll be able to show you similar images from Solar Orbiter as well. Thank you.
Thank you, Daniel. That was a great talk. Really, I mean it. We have seen a lot of game-changing results at a spectacular pace. And thanks for making this tour de force with us. By the way, you broke the record of attendance for ESA online seminars at 264. So that's the new baseline. I think that's a game changer for itself. Now we have time, and Daniel is so kind to be available for questions. There are two ways you can ask your questions. Namely, you can either raise your hand or you can type your questions in the chat. The first question has already been typed there by Robert Jacobson about the comet animation movie, which impressed him so much. And it has already been answered also in the chat by providing the links where he can, where he and you, everybody else, can find these spectacular movies. I see a first raised hand by Roger Bonnet, who has been mentioned in the talk. So, Roger, can you please unmute your microphone and ask your question?
Can you hear me?
Yes, you can. We can hear you very well.
First of all, I would like to really thank Daniel for a remarkable talk. Remarkable talk. It was fantastic. And you did this in the right time, and I'm very impressed, very impressed. I think I just wanted to mention that such a fantastic experiment as SOHO would not have been possible with all the scientists involved. And in particular, I think about my friend and collaborator, Jean-Pierre de la Boudinière, who passed away 3 or 4 years ago, who was the man who made it possible to build the EITs on so many satellites. I would like to thank you, of course, but also Bernard Fleck, your predecessor as SOHO project scientist, and Vicente Domingo, who passed away a few years ago. I have just a question about Solar Orbiter, and you will not be surprised by my question. Is there any contamination already identified or no?
I'm so happy that it looks extremely good in terms of contamination. So we have a specific working group, and as you know, we have these contamination sensors that you helped us get on board. They show extremely little contamination. We saw innocuous contamination in the very beginning. Shortly after launch, there was some water ice that then sublimated. But no PI has complained in any degree about contamination. So I think giving that extra scrutiny really helped.
Thank you very much. That's very good news. It makes my day. Thank you.
Thank you, Roger.
Thank you, Roger. We have time for more questions, both in the chat and by raising your hand. Since I can't see any raised hand right now, let me ask you a question myself, Daniel. It may be a little bit off topic, but I must admit I'm always terribly impressed by helioseismology. When comparing the raw data, which you showed a movie of, and the results, I really flabbergasted that you can come from one to the other. It's just a bubbling, just like boiling water in the kitchen, and yet you can make sense out of it. Now, when you do helioseismology, my question, can you see the planets also have a tidal influence on the sun? Is that visible at all? Is that irrelevant, or is that, I was just wondering if you can see the planets in helioseismology.
To my knowledge, you cannot. I think the signal is too small, but then again, I'm really not a helioseismologist. So I wonder if maybe if Bernard Fleck is on the line, I mean, he would know if someone had attempted successfully to do that.
It may be the signal is too low, and also perhaps the time scale is too long. One or the other. Anyway, it's probably the least important question for SOHO. I can see a raised hand, but I can't see a name. I can only see a number. Saliba, you may unmute the gentleman or lady, and please ask your question.
Yeah, could you please unmute your microphone, please?
Your talking is permitted, but microphone is still muted. Please unmute your microphone. That does not seem to work. Then let's take a question from the chat, from JF, whoever that is. Thank you, Daniel. Question, how many more years of activity for SOHO?
Okay, I think the question means how long will SOHO be operated? I think that's what JF would like to know. The answer is that it depends a little bit on solar activity. The consumables on board are still ample. We have a significant amount of fuel, and we use very little of it. So in terms of maneuver, SOHO has enough fuel for decades. The limiting factor will be the solar arrays, because at a certain degradation, the entire photovoltaic chain will no longer work as before. There were early estimates that gave SOHO until, I believe, 2022 or 23 initially. That estimate has now been raised by a few years. And given the recent lack of activity of the sun, I would guess that at least 5 more years should be possible. And beyond that, I think it's too early to predict, but I think at least for the next handful of years, SOHO should still be able to operate.
That sounds reassuring, and thanks for telling us the story about the American Congress. You said was voting for keeping SOHO alive as long as possible. I wonder how American Congress can influence ESA for funding, but never mind.
Yeah. But lucky, I mean, since NASA is providing most of the support for the operations, that's what really counts, and there is very little expenditure by ESA these days. It's largely personnel, and in particular Bernard Fleck as the project scientist at Goddard for ESA, and a bit of support from experts that help when the spacecraft needs to be maneuvered. But it's very little.
Yeah. So yeah, NASA is contributing a lot. That's true. We have a remark or a question, or rather a remark from Peter Gallagher. Hi, Peter. Thank you, Daniel, for a wonderful talk down memory lane. SOHO spawned a whole new generation of solar physicists by having an open data policy and by having a welcoming, supportive scientific community. Great to see Solar Orbiter continuing this tradition. I think that's a very remark, very well put. Thanks, Peter. Let's see, great talk, Daniel. Which are the 7 instruments that are still working, from Marco Romoli?
Okay, so let's see if I get to all 7. That's a good one. Well, LASCO, of course, as you saw, is still operational. EIT is taking a handful of pictures per day. Then we have the in situ instruments that are effectively all working. So that is, in a way, brings us to 7. So the instruments that are no longer routinely working are MDI, because it has been superseded by HMI on SDO. SUMA and UVCS and CDS reached effectively the end of life as spectrometers. Then we are missing one more that I will have to look up for you.
You can check the movie of this entire talk. I believe it was somewhere mentioned in the talk earlier. A remark from Dipankar Banerjee. SOHO has changed solar physics because of its data policy. It has been said before. I would like to personally thank ESA for that, which changed all of our life. Thank you, Daniel, for an excellent talk. Then Hans Zinnecker asks, do we understand the radial rotation pattern of the convection zone that SOHO found? You were mentioning it in your talk. Do we really understand the radial rotation pattern of the convection zone?
That's a very good question. I believe that solar dynamo models have been, well, refined significantly in the last 20 years to also take these empirical data into account. But the difficult thing is, of course, that if you have a multi-parameter theoretical model, then there are many ways to tweak it in a given way. So I think the question is rather, is there a compelling and unique way why a certain model should have certain parameters set in a particular way? And I think that's always the difficult part about dynamo models, that you could, in theory, get very different, for example, cycle patterns than those observed. So there's still, I think, not a one single dynamo model that would account for all the observables on the sun and not be, let's say, competed against by another model that could explain features in a similar way. So there's still research to be done.
Okay. Bernhard came to the rescue. He writes in the chat, the 7 instruments still operating are Virgo, Golf, LASCO, Swan, COSTEP, Celias, and Ernie. And Sarbani asks Golf, ? And I think, yes, Golf, that's global oscillations at low frequencies. And isn't there a 2017 paper where they came out with the first report of actually gravity modes observed on SOHO, not pressure modes in helioseismology, but gravity modes.
That's indeed right, and that's been, let's say, very interesting, but also much debated result, because gravity modes, I mean, that is in a way the holy grail of helioseismology, to detect modes that do not have pressure as the restoring force, but gravity. They would enable probing the deep solar core, because they go all the way down, and also they need extremely long time series. So this analysis was very careful and detects hints of G modes. But there were, as I understand, also, let's say, objections to whether that result, let's say, that conclusion could really be drawn based on data. So I think the jury is still out as to whether G modes have really been seen unambiguously, but we are still looking.
Fair enough. That's how science progresses. That's the way it goes. Let's go on. Somebody is questioning whether Virgo is still operating, but Bernhard says yes with a exclamation mark. How many SOHO-related papers to this day? I think you said something like close to 6,000.
That's right. I believe it's 5,900 and counting.
Exactly. Yeah, that's what Bernhard also said. I think that's pretty much all on the questions in the chat. There are many. You should later look at the chat. There are many congratulatory messages for you, Daniel, and I can only reinforce these. That has been really a fascinating talk and a real tour de force. So thank you, Daniel, for taking us along on this. Altogether, we still have close to 200 participants. As I said before, we peaked at 264. You set the new record, Daniel. So thanks again, Daniel. As a last item, I would like to point out the continuation of this ESA Game Changers online seminar series. 1 week from now, back at the usual time at 5 p.m., we will have a talk by on Dawn by Carol Raymond from the JPL. 2 weeks from now, there will be a talk on the magnetospheric multiscale MMS mission by Rumi Nakamura, with reminiscences also back to the cluster mission. And 3 weeks from now, I will try to do what Daniel did today for SOHO, but instead for the Ulysses mission. So that's it from us and from ESA today. Thanks everyone for giving us a record attendance. Thank you, Daniel, for giving us this tour de force overview. And thank you, Roger, for attending and for keeping SOHO alive and bringing it back to life after the vacation, as it is called, the SOHO vacation. Thanks, everybody, and bye-bye, and see you in a week from now.
Thank you. Bye-bye.
Yes.